So the final lesson on topic 7. First, we have a look at the data booklet and we see there is a lot of information here. To begin with, it gives us the names and charges of the quarks, so we don't have to remember. Up, charm, top, +2, 3, down, strange, bottom, -1/3 of an electron. And the baryon number is 1/3 for every quark. So when you have 3 quarks together, that means a baryon, you have a baryon number 1. That's another thing that we know from leptons is the charge, -1 to all of them. And all leptons have lepton number 1. Antileptons have lepton number -1. Easy to accept this conservation law of lepton number. This one is more difficult to accept, so I'll put here a question mark. It says all quarks have a strangeness number of 0 except the strange quark. The strange quark that has a strangeness number of -1. And that is quite strange, but it's a law, it's a conservation law, so we'll accept it. We won't look. And then when we talked about the gravitational force experienced by all particles, the mediating particle is the gravitron that we still need to detect. And then the weak force is experienced by quarks and leptons, and these are the bosons, the mediated particles, the photons interacting with charged particles, and the gluons interacting with quarks and gluons, strong nuclear force. These are the 4 forces of nature and the particle. So the periodic table gives us a lot of information. Not this you need to remember, okay? But this is something that we need to have in front of us to solve problems. And then we have to state this 2 things that we need to do before we finish topic 7. One is watch this analogy about the Higgs boson. It was considered the best analogy, so I'm not going to go through it. Just watch it. And it explains how the Higgs interacts with the field. And then the quantum numbers that we need to check the laws in any interactions. The charge number, the baryon number, the lepton number, and the strangeness. These are quantum numbers. They could be +1, -1, or +2/3, or -1/3. Depends. The charge depends on what we're looking at. The baryon number could be also 1/3 for every quark, 1 for any baryon, -1 for antimatter. The lepton number is 1 for all leptons, -1 for antileptons. And the strangeness, it's not always conserved. So this is something that we can also postpone till later, together with the Higgs boson and other strange things. So Feynman's diagram. These are quite simple diagrams, straightforward diagrams to see what the outcomes of interactions between different fundamental particles shows. So it's a representation of an interaction. And there are certain rules that we need to remember. One rule could be the rule that time moves from left to right. Some books have the Feynman diagrams upwards, but let's follow this rule for the examples at least. Time goes from left to right. Any matter particle, any fermion, is represented by an arrow. If it's matter, it goes in the direction of time. If it's antimatter, it goes against time. So this is a positron, and this is an electron. Any boson, any exchange particle, is represented by a wiggly line, curved line. And then the 4th rule, a vertex, like for example this one here, is an interaction. In any interaction there must be 2 straight lines with arrows and 1 wiggly line coming out. And the arrows should point, one arrow should point into the vertex and the other arrow should point out of the vertex. So 4 rules. And the last rule, the most important of all, is that in all vertices, the conservation of baryon number, quantum number, any quantum number must be applied. All conservation laws are true. Examples. An electron absorbs a proton. So let's imagine that this is an electron. Let's use a different color. An electron traveling in this direction, and a photon, energy, interacts with the electron. What creates this? It creates a deflection. So it's still an electron, but the interaction is just between the photon and the electron, changing the trajectory. For example, when you see an electron, this is what happens. You're altering the trajectory of the electron. Just by sending light, the electron is behaving in a different way. This is important to understand Heisenberg uncertainty principle. An electron emits a photon. So in this case, the electron is traveling like this, and all of a sudden, shoot, changes direction and emits. Okay, that changes. Emits a photon. Energy comes out. This is an interaction. So we can look at conservation of charge, conservation of lepton number before and after. This is before. This is after. So this interaction is possible if the quantum numbers are conserved. For example, baryon number here is 0 and here is 0, so it's okay. Lepton number is 1 and here is 1, so it's okay. Charge -1, it's okay. So these laws of conservation give us interactions that are possible. A positron absorbs a photon. Okay, a positron is traveling against time because it's antimatter, and all of a sudden it absorbs a photon. So this is a photon, boom, and the positron probably continues traveling. I'm going to put it black. In a different direction. So this is before and this is after. Another example, pair production, a positron and an electron being produced from a photon. So the photon, poof, all of a sudden creates an interaction, an arrow pointing in, an arrow pointing out. The arrow that is pointing in is a positron. The arrow that is pointing out is an electron. Pair production. Matter popping out into existence from space. What else? David Kahn's wonderful videos, examples of how to solve problems. Please do them. A crash course in particle physics, 13 minutes. This is I can't remember his name. A crash course in particle physics. This. What is the name of the guy? Maria, what is the name of the guy that you love so much?
Brian Cox.
Brian Cox. This is Brian Cox. My wife loves Brian Cox. I don't know if it has anything to do with physics, but she loves Brian Cox. Okay, so this is the last of the lessons in